In this lecture, I am going to explain the Kronig Penney model qualitatively. If you want to see the full detail, then go to description. I have given there the link for full description model. Okay, Kronig and Penney assume the potential as rectangular potential wells. They are periodic in nature, or you can say rectangular potential barriers. They are repeating. You can see they are repeating after some distance. Suppose this is region 1 and region 2. First region is having zero potential, and for region second, potential is V naught, that is maximum potential. Let this is point minus P, this is 0, and this is A. Now, general Schrodinger equation in one dimension is d2 psi upon dx square plus 2m upon h cut square E minus Vx into psi equal to 0. This potential is function of x. Okay, this is one-dimensional Schrodinger wave equation. Now, for region first, we know in this region potential is 0. This Vx is 0. So, Schrodinger equation will be d2 psi upon dx square plus 2m upon h cut square into E psi equal to 0, because this Vx is 0 here. So this is question number 1, and this is for region x lying between 0 and A. When x lies between 0 and A, this is region 1. Schrodinger equation will be this. And for region second, Schrodinger equation will be d2 psi upon dx square plus 2m upon h cut square E minus Vx is V naught here, maximum potential V naught, into psi equal to 0. This is for region x lying between minus B and 0 for this region. In this region, potential is V naught. Okay. Now, we will simplify these equations, these two equations. Let this is alpha square. We will assume this term as alpha square. So, from equation number 1, 2m upon h cut square into E. This is alpha square. Let this is number 3. And from here, 2m upon h cut square into V naught minus E. This is beta square. In this term, we have assumed that V naught is very, very greater than E. So, we have taken 2m upon h cut square, V naught minus E. This is beta square. Now, these two equations will become, equation number 1 will become d2 psi upon dx square plus alpha square psi equal to 0. This is equation number 5, and this is for region x lying between 0 to A. d2 psi upon dx square minus beta square psi equal to 0. This is equation number 6, and this is for region x lying between minus B to 0. Okay, for region second. For these two regions having the periodic potential, F block suggests the solution is of the type psi kx equal to ukx into e raised to power iota kx, where ukx term is also periodic in x. Okay, now if this is the solution of these two equations, then this solution must satisfy these two equations. Okay, so let u1 is the solution for equation 5 and u2 is the solution for equation 6. Then we get two differential equations in u1 and u2. Again, we will have two differential equations in u1 and u2. Now, applying the boundary conditions, boundary conditions. First boundary condition is wave function is continuous everywhere. So u1x at x equal to 0 equal to u2x at x equal to 0. Second condition is if wave function is continuous, then its first derivative will also be continuous everywhere. Then du1 by dx at x equal to 0 equal to du2 by dx at x equal to 0. And third and fourth boundary conditions, these are from periodicity. We know our wave function is periodic, potential is periodic. So u1x at x equal to a should be equal to u2x at x equal to minus b, and its first derivative should be du1 by dx at x equal to a equal to du2 by dx at x equal to minus b. So these two first conditions are from continuity of wave function, and these are from periodicity of the wave function. By imposing these boundary conditions on the above differential equations, we get four linear homogeneous equations with coefficients like a, b, c, d. And from that coefficients a, b, c, d, we will make a determinant. Okay, and the solution of those equations, linear homogeneous equation, will exist only if the determinant is equal to 0. Determinant is vanishing, and from there we will get the equation this. This is equation 7. Beta square minus alpha square upon 2 alpha beta sine alpha a sine hyperbolic beta b plus cos alpha a cos hyperbolic beta b equal to cos k a plus b. Now, this is the complex equation. This is quite complex. So this was simplified by Kronig and Penney by taking some assumptions like V naught approaches infinity when B approaches 0, but V naught into B is finite. V naught B should remain finite. So by imposing this condition, B approaches 0, we get sine hyperbolic beta B equal to beta B, and applying here cos hyperbolic beta B equal to 1. Now put these values in equation number 7, we get beta square minus alpha square upon 2 alpha beta sine alpha A into beta B plus cos alpha A equal to, right hand side will be B is 0, so this will be cos KA. Okay, now from here beta is cancelled, so we get beta square minus alpha square upon 2 alpha sine alpha A into B plus cos alpha A equal to cos Ka. Now from this equation, we will eliminate beta square minus alpha square. We know beta square minus alpha square equal to 2m upon h cut square into V naught minus E. This is the value of beta square, minus alpha square is 2m upon h cut square into E. So we have 2m upon h cut square V naught minus 2E. In starting, we have assumed that this V naught is very greater than E. So this 2E will be neglected in comparison of V naught. So we have beta square minus alpha square equal to 2m upon h cut square into V naught. Now put this value of beta square minus alpha square in equation number 8. We have 2m upon h cut square into V naught B upon 2 alpha sin alpha A plus cos alpha A equal to cos Ka. Okay, 2 cancelled here and we get m V naught B upon h cut square sin alpha A. So this is alpha, we will divide and multiply by A, dividing and multiplying by A plus cos alpha A equal to cos Ka. Now all these values are constant. M is constant, V naught is constant, B, A, H cut, all these are constant. And this term is equal to P. What is P? P is the measure of barrier strength. Barrier strength. And what is barrier? Barrier strength is V naught B. This is barrier strength. And this P is measure of barrier strength. How tightly the electron is bound to the potential well. So this is P sin alpha A upon alpha A plus cos alpha A equal to cos Ka. Equation number 9. So this is the condition for permissible state. This condition will give the permissible values of energy. This is our main equation. And P is m V naught B A upon h cut square. Now if we see the right hand side of equation 9, this is bounded. This is bounded between -1 and +1. The value of cos lies between -1 and +1. So left hand side must remain between -1 and +1. So if we plot the left hand side versus alpha A, P sin alpha A upon alpha A plus cos alpha A versus alpha A at P equal to 3 pi by 2. This is some intermediate value of P. We get a plot like here is alpha A and this is P sine alpha A upon alpha A plus cos alpha A. Okay. Now, right hand side only takes the value between -1 and +1. Suppose this is +1 and here is -1. So we have this is +1 line and this is -1 line. Okay. Now, the plot will be like and so on. Okay. Now, only these values are permissible. Now, only the values shown by these solid lines are permissible. Now, we will conclude from this diagram. Okay. Now, number one is that there are allowed bands. These shaded portion are allowed bands separated by forbidden bands. These are allowed bands. Allowed, and these are not allowed. Not allowed or forbidden. We know in this equation when alpha A equal to plus minus n pi, then cos alpha A will be equal to cos A. This term will be 0. Cos alpha A equal to cos Ka, and Ka will be equal to plus minus n pi from here. Okay, and K will be equal to plus minus n pi by A. Okay, so we can show that these allowed and not allowed bands are separated by boundaries k equal to plus minus n pi by A. There will be boundaries at k equal to plus minus n pi by A. Now this alpha A, which is energy, because alpha square equal to 2m upon h cut square into E, and E will be alpha square h cut square upon 2m. So E energy is depending upon alpha. So this alpha A will represent the energy here. Okay. Now as alpha A increases, the width of the band, allowed band, is increasing. Second point is, as alpha A increases, the width of allowed band increases. And if alpha A decreases, the width of allowed band decreases. Third case is when P approaches infinity. If P approaches infinity, then left hand side will be infinity. So to make it finite, sine alpha A should be 0. Sine alpha A should be 0. And sine alpha is 0 when sine n pi. Okay, so we have alpha A equal to plus minus n pi, or alpha equal to plus minus n pi by A. From here, alpha square equal to n square pi square upon A square, and also alpha square equal to 2m upon h cut square into E. Now from here, E equal to n square pi square h cut square upon 2m A square. So we can see clearly from here that E is independent of K, and we get discrete energy levels here. We get here discrete energy levels. This result is similar to the energy levels of the particle for a constant potential box of atomic dimension. If P is large, then the tunneling of electron is almost impossible. The electron cannot penetrate the potential well. Next case is when P approaches 0. When P approaches 0, this first term is 0, then cos alpha A equal to cos Ka, or alpha A equal to Ka, or you can say alpha equal to K, or alpha square equal to K square, and this is equal to 2m upon h cut square into E. So we have E equal to h cut square K square upon 2m. Now, if we put the values of h cut, which is h upon 2 pi, K, this is 2 pi by lambda, we have h square upon 2 pi square into 2m, 2 pi square upon lambda square. So 2 pi square cancel, and here lambda equal to h upon mv. So h square upon 2m into m square v square upon h square, putting the value of lambda square. So this will give E equal to 1 by 2 m v square. This is the energy of a free particle. So this energy is similar to the energy of a free particle. In this case, when P is 0, the electron can take any values of energy. This diagram shows the different permissible energy values with respect to P. When P approaches 0, the particle is free and all the levels are allowed to it. For the intermediate case, we get allowed bands separated by forbidden bands, like in the case of P equal to 3 pi by 2. And when P approaches infinity, then discrete energy levels are there. The electron is tightly bound to the potential well. So this was all about Kronig Penney model. Thank you.